Hello everyone, welcome to the course on Digital Design with FPGA. I am Dr. Pratiksha Raut, Assistant Professor in the Department of EC at Siddharth Academy of Higher Education, deemed to be University Vijayawada. So in this lecture, we will begin exploring about the Programmable Logic Devices or PLD, which forms the foundation for digital system design using FPGA, we are going to discuss. So coming to our topic, let us discuss about the programmable logic devices. So what is the programmable logic device? So here you can see the logic diagram of PLD, where we have the input as a logic variables, and the middle of the block contains the logical gates and the programmable switches, and in the outside we have the output just like the logic function. So what are PLD? PLDs are nothing but the programmable logic device, which are the integrated circuits that can be unprogrammed to or programmed to perform logical operations. Unlike fixed function like ICs, PLD offer reconfigurability, meaning their behavior can be defined by the user after manufacturing. Also, they enable fast prototyping, and we can design very flexibility, and it can be also reusable. That is the key features in the modern digital system of PLD. So here we are now going to discuss about PLD programming. So what do you mean by PLD programming? The programming of PLD involves writing a configuration using a computer and downloading into a device with a PLD programmer. Here you can see the PLD where it contains the system and a JTAG cable and the programmable device. So the code can be downloadable into a devices using a standard cable. Okay, so this is commonly done using JTAG cable, and which will act as an interface for boundary scanning and also the device configuration. Once programmed, the PLD operates as a custom logic device tailored to your application. Now we are going to see, so what are the various PLD? So we have PLD as three types, that is programmable read-only memory, programmable array logic, that is PL device, and the programmable logic array PLA device. So in PROM, we have either AND gate or OR gate, because many of the digital system contain basic gates as AND or OR. So based on this AND and OR gate, we have three types. So coming to PROM, we have a AND gate as a fixed and OR gate which is programmable, that means which can be changed. And coming to PAL device, that is programmable array logic device. Here we have a programmable AND array and fixed OR array, that means OR array cannot be programmable. Coming to PLA, that is a reverse of PAL, that is AND array is programmable but the OR array is also programmable, that is inputs programmable AND array, programmable OR array, and the outputs. So we have understood there are three types: PROM, PAL, and PLA. So now we will simple understand the notation of PLD. How can we understood that it is a PLD? Some symbols are there where we will, and so while designing or reading a PLD diagram, some specific notation is used. Each gate is each gate is shown with a single input line. Input signals interact this line at a right angles. A cross which is shown at a junction means that is a fusible link is entered, that is connection is made. The cross, that is ABC, that means here the connection is made where the input and the output. Absence of a cross means there is a no connection. If connection is there, then a cross symbol indicates a connection. If a cross connection is absent, that means there is a no connection. That means it is zero. So a dot and intersection means it is a hardwired connection. If all the input fuses to a gate are intact, let me mark a cross inside the gate. So now we can understand that if cross symbol is there, that means there is a connection, and if there is no cross symbol, there is a no connection. So this is the general notation of the PLD devices, and which connects from input to output. Here also you see lack of cross indicates the fusion is blown or no connection exists. Here you can see the figure D, there is a no connection. That means there is a no connection in the input C. because it is broken. And in the first figure we can see in B there is a no cross connection. That means B is not connected to the as an input to a gate. And here earlier we discussed dot connection means is a hardware connection. That means that is not fusible is indicated by a junction dot. Now let us discuss about the programmable read-only memory, that is PROM. So PROM is the simplest form of PLD. It contains a fixed decoder or addressing and programmable or array that stores the output logic. Each input combination selects a specific memory word that determines the output. And prompts are great for implementing combinational logic directly from truth tables, but they require more memory if the logic is not minimized. Here is a simple example of PROM logic. Thereafter, we can discuss how to design the programmable read-only memory. These are the simple numerical problems. Later we can discuss. So now we come to PLA, that is programmable logic array. So PLAs are more flexible than PROM. Now we are discussing about the theory about PROM, PLA and PLA, and the numericals we will discuss it later. So coming to PLA, they include both programmable AND array and programmable OR array. And this is the logic diagram of PLA. And this structure will allow you to create custom logic function efficiently. Unlike PROM, PLA don't require any output to be canonical mean term. And the logic is minimized using Boolean algebra or K-maps, as we have discussed earlier before being implemented into PLA. Now let us know the difference between the PROM and PLA. So PROMs are easy to use since we don't have to minimize the logic, and they store all possible combinations. And PLA requires logical minimization, but they are more efficient in terms of space and speed. And also designers choose between two based on optimization, flexibilities, and area constraint. This is a simple logic example of logic design example, where this slide show an example logic function using a PLA. You can see how inputs are connected to the product terms using AND gate, and those are summed through OR gates to create the output. So including complementary variables, we can reduce the number of product terms needed. This is a simple PLA table, where PLA table is used to specify input section, how inputs connected to AND gate, output section, how outputs of AND gate to the OR gate. TC means true or complemented. So whether the TC section will show you whether the output is true or complemented form. So each row in this table represents a product term, and the table format simplifies the programmable process. Now let us discuss about the PAL. So PLs are simple and faster than PLA. They use a programmable AND array but a fixed OR array set by the manufacturer. Because of the fixed OR logic, PALs are easier and cheaper to fabricate, but these are less flexible because we cannot use the OR logic, means they are fixed. We cannot reprogram them. In our example, you see we have a 4 input 3 output PAL device which can handle 3 expansion with limit on product term. So this is the internal structure of PAL. Inputs goes to AND gate, we generate the product term. This product term then will go into fixed to OR gate, because OR gate are fixed here to produce the output. You can see how it's more constrained in PLA but still powerful for many applications. Now in this slide we will summarize the difference between ROM versus PLA versus PAL. So when we see this table, what we can compare is that ROM is simple and also it stores mean term, but it is inefficient. But PLA offers flexibility, full flexibility at the cost of complexity, and PLA offers reduced complexity but with limited logic. The choice depends on the logic functions based on requirement of space and speed. Either we can use PAL, PLA or PROM. Now one more logic devices we have other than PLD, which are known as sequential programmable logic device. Up to now we have seen only combinational PLD, but how can we generate the sequential devices? So for designing of sequential programmable logic device, we have a special type of PLD that are known as SPLD. So this SPLD can store state. That means state we know, right? In the flip-flop we have the S0 state, S1 state. In the register we have S0 state, S1 state. So these states are retained in the SPLD devices, which will make them usable for finite state machine, that is Murray machine. So this contains the number of states. So how these states are state by using SPLD, and these are used for making machines, counters, and memory based logic. So these devices output values based not only on current input but also on the past state, just like the sequential device. But in a combination, they depends only on the present input. But these devices depends on present input as well as the past output, because we know all the difference between what are combination circuit and what are the sequencer circuit. Combination circuits are the AND gate, OR gate, NOT gate. But coming to sequencer circuit, we have a memory where output depends on the present input as well as past output. And the examples may be flip flop, counter, register, etc. Already you know in the digital circuit design system. So let us discuss about the SPLD internal structure. As we saw, now PLD consists of only gates. So only combination circuit design is possible. But coming to SPLD internal structure, they have each block called as a macro cell. So each block contains combinational AND or OR logic and a flip-flop. Either they contain JK flip-flop or D flip-flop. A multiplexer for output control. That means the output can be controlled in the SPLD device by using a multiplexer. And so in overall, this setup will allow for both combination and sequential logic implementation in one unit. So SPLD are far better than the PLD. As we discussed, macro cell is a simpler unit of the SPLD. So let us discuss about what is a macro cell. So we normally each macro cell will contains input signal through AND and OR array, because generally we will give inputs and the output will generate. So from where the input signals will go through AND or OR array. Now these inputs will be fed as a result in a D flip-flop. As we discussed, it uses either D flip-flop or JK flip-flop. So these inputs are fed in the D flip-flop triggered by a clock edge. As we know, when clock pulse is one, the circuit will start working. So now the output will passes through a multiplexer, because it is a controlling unit by an output enable signal. So feedback from the flip-flop can also be used as an input, allowing complex sequential behavior. So this is all about SPLD. SPLD is sequential programmable logic device which contains the sequencer circuit like flip-flop and register controlled by a multiplexer, and the inputs are given by a AND or OR gate and controlled by a multiplexer. So this is the block diagram of macro cell. You can see these are the inputs, there are the logic gates. Now we have a D flip-flop and the output contains a multiplexer to be controlled. As we already discussed, this is a written explanation. D flip-flop is edge triggered and changes state on clock edge, and the output is controlled by a mux, and the output of flip-flop is back to the input by an AND array. And also in one IC, normal SPLD will contain 8 to 16 macro cell. So now we'll discuss, apart from SPLD and PLD, we have one more is complex programmable logic device. So what are CPLD? It contains multiple logic blocks and they have an input output for communication. It interconnect fabric for routing the signal. Each logic block can hold up to 8 to 16 macro cells. So it is suitable for medium scale applications such as decoders, encoders and control units. So what are the features of CPLD? Let's break down the CPLD architecture. Logic cells. These are the basic building blocks with AND or XOR and flip-flop. And as we studied, they have multiple macro cells in them. So macro cells contains a group of logics with added features. Input output block CPLD with outside world, and outside world, that means it will connect with the external device. Programmable interconnects, so which will route the signal flexibly inside the chip. So this structure gives CPLD both the flexibility of PLD and also the power of customizing. You can now see the structure of typical CPLD architecture: interconnection wire, PAL-like block in input-output block, and interconnected. Digital system design requires several PLD. CPLD is a collection of individual PLD on a single IC. Each individual will contain 8 to 16 macros, and PF directs the input to the individual macros simulation to output. So these are the explanation what I've already explained in the previous slide. What are logic devices, macro cells, input output block, and program connect, as we've seen in the previous structure. So this is all about the PLD, SPLD, and CPLD. Basic types are of PLD are PROM, PLA, and PAL. Conclusion: sequential PLD and macro cells attain the complete PLD, CPLD, and architecture, and we have understood the device as a very crucial as they form the basis of more advanced system like FPGA, which will cover in the upcoming lecture.